So in this podcast, we'll have an overview of the ionic bonding model and talk about what happens to electrons and how they fit together, how the energy is involved, and what happens to the properties of ionic compounds because of how it bonds. So the central idea of the ionic bonding model is that electrons are transferred from metals, which form cations, to nonmetals, which form anions. And here we've done the Lewis dot symbols to show the formation of ionic compounds through electron transfer. So we're doing this in great detail to show how the compounds form. So if you've got lithium and fluoride, lithium has one valence electron, fluoride has 7, so one electron gets transferred from lithium to fluoride, so that lithium is a cation, it's lost its electron. Fluoride has gained one, it's an anion. And because the charges are balanced, +1 and a -1, they add up to 0, so the overall charge is neutral, and it makes lithium fluoride the compound. If you've got subscripts, things are a little bit more complicated. Sodium and oxygen. Sodium has one valence electron, oxygen has 6, so they don't add up with 1 and 1, so we need 2 sodiums. Each sodium is going to lose its valence electron, give it to oxygen, so then we have 2 sodiums, each with a +1, 1 oxygen, it has a -2. Everything is going to add up to 0 and be neutral overall. So 2 sodiums, 1 oxygen, Na2O is the formula. Last one, aluminum and chloride. 1 aluminum has 3 valence electrons. Each chloride has 7 and needs 1. So we need 3 chlorides for things to balance out. 1 aluminum with a +3, 3 chlorides, each with a -1. They all add up to 0. And we get our formula, aluminum chloride, AlCl3. The electron transfer process, we're going to talk a little bit about energy. The electron transfer process is usually energetically favorable, which means it happens without us adding more energy. Enthalpy is the way that we measure energy, and it's called H for enthalpy. And it refers to the internal energy of our system. We don't usually talk about H. We almost always talk about delta H, which is the change in energy. So we'll talk about this a lot. If delta H is negative, what this means is that it has a negative change. It starts out up here. As the reaction goes, it's going to end up in a lower place, which means that change is negative, and this means that the reaction is favorable because it releases energy. And you can think about it like a ball that's rolling downhill. It's going to happen without us adding energy to it. It's going to have leftover energy. It's going to be favorable, and we call this a negative delta H. If delta H is positive, everything is going to be the opposite. Here's our reaction scheme. It starts out down here. It's going to end up higher. So it's a positive change, positive delta H. This reaction is unfavorable, which means we have to add energy to make it happen. It's not going to happen without additional energy. So we've already talked about ion formation when we talked about the periodic table. There's 2 processes that have to happen. The ionization energy is the energy to remove an electron from the cation. So X is going to be the cation. It loses an electron and makes X with a plus charge. Electron affinity is the energy involved to add an electron to the anion. So energy to add an electron, Y is our anion, +1 electron, and it gets together and makes an anion. So both ions have to form, and there's energy involved in both processes. But then what happens is the 2 ions are attracted to each other because they have opposite charges. This is affected by the charge number, and that's the absolute value of the charge number. If it's a higher number, then it's going to be more attracted. There's going to be more attraction. Also, the distance between the ions, if it is a smaller size, if the ions are smaller, there's going to be more attraction. Everything gets together, and the lattice energy, which is the energy of the whole thing forming, the whole ionic compound forming, is a combination of ionization energy, removing the electron from the cation, electron affinity, adding the electron to the anion, and then there's energy released when the bond forms. So bond formation energy, that is a favorable process. This can be summarized in something called Coulomb's law, which says that energy is equal to a constant times Q1 times Q2 divided by R, where R is the charge on the ions, and again it's the absolute value of the charges, so the higher they are, the stronger the energy is, and then the distance between them divided by R. So if the distance is smaller, if the atoms are smaller, the distance is going to be smaller, and the because it's divided by E, or by R here, energy is going to be higher. Again, this says the same thing. Effective ion size, smaller ions mean higher attraction, higher lattice energy. And what this means is that if you have atoms that are smaller and they have higher lattice energy, they are going to have higher melting points. It's going to take more energy to make them melt. The bonds are going to be stronger. Again, higher charge number, more attraction, higher lattice energy. This diagram here is showing the ion size. So lithium is the smallest, then sodium, then potassium, then rubidium, and you can see for the small ones, lithium is the smallest, and it forms the tightest bond, the strongest bond with fluoride, because everything is so tiny that it's going to have the highest melting point. And then as the atoms get bigger, the melting point is going to go down. So here's the anions. Fluoride is the smallest, then chloride, then bromide, then iodide. So the strongest lattice energy is going to be from the smallest cation plus the smallest anion. That's going to be lithium fluoride up here. Highest melting point. The lowest melting point, weakest lattice energy, is going to be rubidium, which is the biggest cation, combined with iodide, which is the biggest anion. So that's going to be all the way down here. How does the lattice structure of an ionic compound help explain their properties? Ionic compounds are brittle. If you hit them with a hammer here, they're going to shatter. And why does that happen? Because they're arranged in this lattice structure. You hit it with an external force here. As you hit it, the cations bump into each other. And then what happens is you've got cations next to each other, anions next to each other, and it causes them to crack. So then they're going to break apart and be really brittle. Conductivity is also a factor that comes from ionic compounds. In order for current to flow, you have to have moving electrons. And ionic compounds conduct if they are in solution, dissolved in water, so yeah, the ions can move around. It conducts here. Or if they're melted, we call that molten salts, and the lattice structure is broken, things are melted, and the electrons can move around. And this is also going to conduct electricity. It conducts very well. In the solid state, they don't conduct electricity because the electrons do not move.